In this lesson, we're going to discuss how to factor quadratics. And the different techniques we're going to look at: factoring out the greatest common factor, factoring with the difference of squares formula, and also the sum or difference of cubes formula, the process of factor by grouping, quadratics where a is equal to 1, factoring special products, quadratics where a is not equal to 1, and then we'll answer the age-old question is, why is factoring hard? Now, one thing I want to state before I get started is 1 through 5. All of these methods are not too difficult. And actually is the majority of the types that you run into when you need to solve a problem with a quadratic. The only one that can be tricky, and it's not always tricky, is this one right here. The problem is, students seem to remember this one the most and think that the entire process of factoring is difficult because of that one case. 1 out of 5 being difficult doesn't really make the whole thing difficult. If you can handle these right here accurately, you can factor just about everything you're going to need to be able to factor. And then we'll talk about number 6 when we get there. I have a couple of ideas to help make that a little bit more manageable. Let's start with quadratic expression. So a quadratic expression is any mathematical expression that can be written in the form ax squared plus bx plus c, where a does not equal 0. Notice there's no equal sign in this, otherwise that would be a quadratic equation, which means you would have to solve it, and you get x by itself when you're solving. So here we're not solving, we're just factoring. So a couple of examples of quadratic expressions. All right, this one definitely qualifies. So if we have x squared plus 4x minus 3, the coefficients a, b, and c you want to be able to identify. So in this case, a is the term multiplying your squared variable. So in this case, it's just understood to be positive 1. Now, this is also called a leading term coefficient. And that's important. That's a very important term to remember because we say that quite a bit, referring to the coefficient on the in a quadratic, the term that's squared. But if you have higher degree polynomials, it's the whatever the term that has the highest exponent, the coefficient on that particular term. So the leading term coefficient. B for a quadratic is just the number multiplying x. So in this case, it's a positive 4. And then c, in this case, is negative 3. This is also called the constant term, or just the constant. So leading term coefficient and constant, those are important terms to remember. We'll use those throughout this lesson. Another example. So this also qualifies as a quadratic expression, but if you'll notice, it's not really written in the form that we have exclusively. However, there's 2 like terms here that could be combined. So 4x squared minus 8x plus 10. Now it's in the form of a quadratic. So if it can be written in that form, it counts. Okay? So in this particular situation, we have a is equal to 4, b is negative 8, and c is 10. Okay, so when you're identifying a, b, and c, make sure you understand or watch out for positives and negatives. Now, another thing to note is that this is also equal to, say like negative 8x plus 4x squared plus 10. So I can rearrange these terms and the meaning does not change. The meaning is still the same here. Now, as the last example, here's another quadratic. The important thing is the squared variable. So up here where it says, ax squared plus bx plus c, where a does not equal 0. It doesn't say that b and c can't be 0. They absolutely can. So in this case, a would be 1, b would be 0 because there's no term multiplying x, so we just assume that's just 0. And c is the constant negative 6. All right, so that's perfectly acceptable as well. Now, let's talk about some factoring techniques. First thing you always want to do when approaching a quadratic to factor is to look for any greatest common factors that you can factor out. So for instance, with this quadratic, 9x squared plus 18x. Look to your constants first and see if there's a number that evenly divides all of your constants. So for instance, 9 and 18 are both evenly divisible by 9. So 9 as part of my greatest common factor. Now with the variables, it's actually a little bit easier because the variables are already factored. The numbers can be tricky because sometimes you have to kind of factor them either in your head or off to the side to figure out what the greatest common factor is. The variables are already factored. You just take whichever variable has the lowest exponent. So for instance, between x squared and x has the lowest exponent. So that's going to be part of your greatest common factor, which is somewhat confusing. Students often say, well, if it's the greatest common factor, why wouldn't I use x squared? Well, the issue is you're going to divide your terms by your greatest common factor. So if you used x squared, your final answer, you want to not have any fractions in it. Well, 9x squared divided by 9x squared is 1, that's fine. 18 divided by 9 is 2, that's good. But x divided by x squared is divided by x. So now I have a fraction. I don't want to purposefully put fractions into the problem that don't exist in the first place. So it does sound counterintuitive that the greatest common factor would include the smallest exponent, but that's how it works. It's the largest factor that is divisible by all terms. And so now what you do is basically divide out that term, or we call it factoring it out. And so, if you take the first term, 9x squared, and divide it by 9x, well, that's going to cancel the 9's. X squared over x leaves you just x in the numerator. So x is left over in that first term. Then if you have 18x divided by 9x, 8 over 9 is 2, x divided by x cancels out. So then I'm left with 9x times x minus 2. So that's factored the greatest common factor out. Here's a slightly more complex example. So for the GCF, let's start with the numbers. We have 6, 2, and 10. The largest number that's divisible by all of those numbers and results in an integer value is 2. 6 divided by 2 is 3, 2 divided by 2 is 1, 10 divided by 2 is 5. It's the largest number that will divide all of those evenly. Now for the variables, a only appears in the first term. It's not part of the GCF. B only appears in the second term. It's not part of the GCF. X, however, does appear in every single one of the terms, but the largest exponent on the x's is 1. So the largest exponent for all the x's. I'm sorry, the smallest exponent for all the x's is 1. So that's what the GCF is. So I'm going to factor out 2x from this polynomial. So 6a x cubed divided by 2x would be 3a x squared. Now if I take 2b x squared divided by 2x, the 2's cancel. I have b and x left. And if I take 10x divided by 2x, that leaves me with just a 5. So now I've factored out that GCF. Now, a lot of problems don't have a greatest common factor other than just positive 1. So you kind of get out of the habit of looking for them, but it's really important to always look for greatest common factors. But in this situation, there's no value that's divisible into each term. So the GCF is just 1, so it just doesn't factor any further. And that's fine. That'll happen. You just need to be able to recognize when that happens. Now here's another situation that's a little bit tricky, but extremely useful, as we'll see later on in this video. The GCF doesn't have to just be a single term. It can be a quantity inside parentheses, as we have right here. The GCF here can be the quantity b minus 2. That's perfectly fine. So basically, I'm going to factor out b minus 2 from each one of these terms. Now if I come off to the side to show you, if I take 3b times b minus 2 over b minus 2, that entire quantity cancels out, so this reduces to 3b. And then if I have 2 times the quantity b minus 2 over b minus 2, this entire thing cancels, and this term reduces to positive 2. And so that is also a way that we can take advantage of a greatest common factor. We'll see its importance later on. Now, after you've factored out a greatest common factor, the next thing you want to do is just count the number of terms in the polynomial you're trying to factor, because that really does decide what technique that you need to apply. If there are 2 terms, chances are you will be using the difference of squares. And if you recall that formula, it's a squared minus b squared equals the quantity a plus b times the quantity a minus b, which you can check through the process of foiling, but that is how it works. So for example, if I have x squared minus 9. If you'll notice, each one of these terms are perfect squares. And that's where you recognize that the difference of squares formula gets applied, because here, each of these terms are perfect squares. So the square root of x squared is just x, the square root of 9 is 3, and that's what I use in these parts right here, the square root of those numbers. So I just write this as x plus 3 times x minus 3, and that is my factors. And you can absolutely check that that works if you want through foiling. So basically, if you multiply x times x, that gives you x squared. X times negative 3 is minus 3x. Whoops. Oh, that's way too big of a eraser. That's better. All right, so then if I do 3 times x, that would be plus 3x. And 3 times negative 3 minus 9. These two cancel, and I'm left with x squared minus 9. So that was indeed the factorization. All right, let's try a slightly more advanced example. So the idea is you just need to recognize if you have 2 terms and both happen to be perfect squares, find the square root of each of those, and it is important that they're subtracted, Okay, that needs to be a minus. And then express your answer as the sum of the square roots times the difference of the square roots. These are called conjugate pairs of one another. All right, so it's pretty easy to apply once you recognize when it will apply and how to do so. So here's a more advanced example. These are both perfect squares. So for instance, x to the fourth is the same thing as x squared squared. 16 is the same thing as 4 squared. So this would factor into, and I'm sorry, I should have said, they are subtracted, that's important. This will factor into x squared plus 4 times x squared minus 4. And the thing to note here is this polynomial right here, it is another iteration of the difference of squares, because x squared is a perfect square, 4 is a perfect square. Now, they're subtracted, and so I can do another iteration of the difference of squares. So this becomes x squared plus 4 times x plus 2 times x minus 2. And you may be wondering, why didn't I do the same thing here? Well, the problem is we don't have a sum of squares formula. It doesn't factor into rational numbers, and rational numbers are either integer values or fractional values. It can factor, and you'll see it factor later on, but it factors into complex values, which involve the square root of -1, which you may know as the value I. But for now, we're only factoring into real numbers. And so this is the x plus s squared plus 4 will not factor into real numbers. Right? Here's a slightly more advanced looking example. But when you get down to it, there's nothing more difficult here. 81's x squared, its square root is 9x. The square root of 100y squared is 10y. So even though there's two variables here, it works the same. You just write 9x plus 10y times 9x minus 10y. All right, now I mentioned earlier the x squared plus 4. Just want to bring it up again. This is what we call a prime polynomial for real numbers, because it won't factor into any other real numbers because of this plus in between. Similarly, x squared plus 5. Oh, I'm sorry, x squared minus 5. It is subtracted, but the thing is, x, even though that's a perfect square, 5 is not a perfect square. You could write it with the square root of 5 and express it x plus the square root of 5 times x minus the square root of 5. Just like up here, you could express this as x plus 2i times x minus 2i. Right now, when we're talking about factoring, we're factoring into rational numbers. And rational numbers can be written as a fraction. So these are irrational, and these are irrational. So as far as we're concerned, both of these are examples of prime polynomials. Now, it depends on your application. If your application allows you to use irrational or complex numbers, then it's no longer prime. You can factor it. But for rationals, these are both prime. Now, next up, we have formulas for the sum or difference of cubes. These get used much less often than the sum or difference of squares. Those are much more important equations. They are generally easy enough to remember the form of them. So it's always like, you know, a squared times ab, and b squared. So it's easy enough to kind of remember the form of it. The thing that's kind of difficult to remember here are these signs. Well, there's one way of remembering these that's nice. It's this mnemonic SOAP. And so what it means is this sign right here is always the same as this sign. So those always match. This one is opposite, and this one is always positive. So that's where the mnemonic comes in. So same, opposite, always positive. So SOAP. So that might help you out. We're just going to do one example of this real quick and then move forward because, as I said, this doesn't really show up a whole lot. So the cube roots here are x and 2. Oops, don't know why I wrote x and x. So the factorization, it's x and 2. This sign is always the same as my original sign. Then it's the first one squared, then the 2 multiplied, and then the second one squared. Then it's the opposite of the original sign and always positive. And there we have it factored. Next up, if you count your terms and you find that you have 4 terms in your polynomial, well then the only thing that's going to work, if it will work, and it doesn't always, is factor by grouping. So for example, if I have 7x minus 7y plus bx minus by. The way factor by grouping works is you group together 2 terms and the other 2 terms. And it generally doesn't make a whole lot of difference which terms you group together, as long as the 2 groups contain some sort of common factor between them. So for instance, the first 2 have a common factor of 7, and I can factor that out. And then the second 2 have a common factor of b, so I can factor that out of the second group. And if you'll notice, I'm in this situation where the quantity x minus y is a common factor, and I can factor the x minus y out of these 2 terms, and I'm left with 7 plus b when I remove those. So that is the process of factor by grouping. Here's another example of that. So occasionally you could run into a cubic equation, and we generally don't have methods of factoring cubic equations, but if there's 4 terms, factor by grouping may work for you. So for instance, if I group together the first 2 terms and the second 2, I'm going to put a plus in between and leave that negative with my 10. If I didn't do that, then I would have to make sure I'm pulling out a negative from the 5 as well. Okay, so just leave the negative with that value. If you need to, put a plus in between. In the next step, there's a common factor of x squared in the first set of parentheses, which will leave me with 2x plus 1. Then there's a common factor of negative 5 in the second set, which leaves me also with 2x plus 1. Now the reason I pulled out negative 5 is because whenever this leading term inside here is negative, I want to pull out a negative, because you always want your leading term after your factoring to be positive. And if you'll notice, just like in the last example, 2x plus 1 is a factor which can be pulled out, and then I'm left with x squared minus 5 for the remaining pieces. So those come from, in case you aren't seeing this, there's the x squared and there's the minus 5. All right, and x squared minus 5, doesn't factor into rational values, so we're finished. If it had been x squared minus 4, we would apply the difference of squares and continue the problem and factor it completely, but that's not the situation in this case. Now, factor by grouping doesn't work for every single polynomial that has 4 terms in it. So this is basically the same as the last example, but just slightly different. So what I'm going to do is group together the first 2 terms and the second 2 terms, just like I did in the last example. Now I'm going to factor out x squared from each one. And from the second set, I'll factor out negative 5. So that's going to leave me with 2x minus 3. Now here's the thing about factor by grouping. If these 2 terms don't match, you can't do factor by grouping. You can't pull that out. So essentially this is as factored as we're going to get it. So it's usually a rare case that factor by grouping does work, so you don't want to count on it happening all the time. But if you have 4 terms, that's probably the only thing that's going to work for you. All right, now we're into what happens when you have 3 terms. Well, we're going to deal first with the simplest case when you have 3 terms. That's when a is equal to 1. So what I mean there is, if you have the original quadratic ax squared plus bx plus c, when a is equal to 1, it reduces down to just x squared plus bx plus c. And factoring is generally pretty straightforward in that case, because you're just looking for 2 numbers whose product is c and whose sum is b. So, for example, x squared minus x minus 6. Well, I'm looking for 2 numbers that multiply to negative 6 and add up to negative 1. So the factors of 6, we have 6 and 1, and we have 2 and 3. So I think 2 and 3 are on the right track, but we have to make sure the signs work out as well. And so we have 2 and negative 3. That'll work out perfect. So the factors here are just going to be x plus 2 times x minus 3. So there's nothing at all difficult about that. The only thing that can make this difficult is if the numbers involved here, there and there, are large numbers or have a whole lot of factors to try, or But in general, that's about as difficult as this gets. Now, one thing that I want to show you is, first, let's make sure these are the correct factors. So let's check it. So if I use FOIL, let me write it back over here. So if I use FOIL to check this, x times x is x squared, x times negative 3 is minus 3x, then I have plus 2x and minus 6. So x squared minus x minus 6. So that checks out. Now, let's answer a question. Why does this work? Because it's always important to kind of understand what's going on behind the scenes, even if you generally will be skipping those steps. So the reason this works is if I take my original polynomial and I split this term up into plus 2x minus 3x and minus 6. So all I've done is just taken my original polynomial and written it using these 2 numbers. Just kind of decompose my middle value into those 2 numbers. Now if I group the first 2 values together and the second 2 values together, x times x plus 2 minus 3 times x plus 2. Factor by grouping will work here. And I end up with x plus 2 times x minus 3. So all of these steps are going on behind the scenes, but it's perfectly okay to just jump straight down here. All right, it's actually a whole lot faster. But that's the reason why this is working the way it does. It's not something that's magical here. We just don't generally see those steps. All right, and from now on, we won't really be writing those steps. We'll just get our answers faster. All right, so in the next example, I'm looking for two numbers that multiply to positive 7 and add to positive 8. So 7 and 1 look like my only options. And I'm finished. Very easy in that case. All right, now in this example, I'm looking for two numbers that multiply to 24, but then add to negative 4. So for 24, if you think about all the factors of 24, you've got 1 and 24, 2 and 12, 3 and 8, 4 and 6, 5 won't divide it, and then when I get to 6, I've already listed it, so I don't need to mark it again. So you're looking for values that would add to negative 4. So 1 and 24 could be 25 or 23, so that's no good. 2 and 12 could be 12 or 10, so that's no good. 3 and 8 could be 11 or 5, so that's no good. 4 and 6 could be 10 or 2. So that's no good either. This is entirely a possibility. And don't pull your hair out trying to come up with more factors. Once you've tried all the different factors of 24, then you can comfortably state that this is a prime polynomial. This will not factor into integer or rational values. It will factor into probably irrational or maybe complex numbers, but that's for another day. For now, we just call it prime. All right, this next example. Notice, before we start this, that there is a greatest common factor of 5 within this problem. And you want to pull that out because it's going to make your problem simpler. It's not that you wouldn't be able to solve it without pulling it out, it's just a whole lot harder. So my numbers are all a whole lot smaller and thus easier to work with. So 3 and 1, if the 3 is negative, everything will work out fine. So this factors into 5 times x minus 3 times x plus 1. All right, one last example. The reason I've chosen this one is because the leading term here is a negative number. When your leading term is negative, the very first step in your problem should always be to change all the signs in your polynomial, factor out a negative number, that is. Otherwise, you have to remember the opposite of every rule that you've just learned. It's much easier to factor out the negative to begin with. So now I'm looking for numbers that multiply to negative 54, but then add up to negative 3. So let's see. For 54, 6 and 9 will work here. So 9 is negative. So we have negative y plus 6 times y minus 9. And there we have it factored. All right, there's other situations you run into if you have 3 terms. The one we just looked at, where the leading term is equal to 1, that's the easiest case. The next easiest case is when we have special products. So these are called perfect square trinomials, and if you identify that the first term and the last term are perfect squares, and you double check that the middle term works out, then you can actually factor very complex looking polynomials rather easily as well. So for example, this right here. So x squared is a perfect square, 81 is a perfect square. The only thing I need to check is that middle term. So the middle term is of the form 2 times the first times the second, because it's 2ab. So this would be 18x. Since it checks out, we're good. So this is going to factor into x plus 9 quantity squared, x minus 9 quantity squared, because there's a negative right there. So it's going to be an x minus 9. So it's pretty straightforward when it does apply. So let's look at even more intimidating looking example here. Again, I notice this is a perfect square. So it's the square of 2x. And this is a perfect square, the square of 5y. So we just need to check 2 times 2x times 5y just has to equal this middle term. So what happens? 2 times 2 is 4, 4 times 5 is 20, and then we have the xy. Great, it works out. So this just becomes 2x plus 5y quantity squared. So those are all the simplest of cases. Now we're going to look at the more difficult case. 3 terms where the leading term coefficient's not equal to 1. Now you generally have to do some sort of guess and check method. And the guess and check method is pretty easy to do as long as there's not many possibilities to guess and check. Like if these two numbers are prime numbers, there's only 2 possible polynomials that this could factor into. So you just have to check and see which one works. So for instance, we're going to guess that the first 2 terms, their product has to be 3x squared. So we're going to guess that the first 2 terms are 3x and x. Those are the only 2 things that are going to multiply to 3x squared. Now the second 2, I could either have 1 and 5 or 5 and 1. But since those numbers are prime, these are the only possibilities. So I just kind of have to check the middle term and see what would work out. So if I did 3x times 5, that would be 15. And 1 times x would be x. Well, no matter what I do in terms of positive and negative numbers, I can't get those 2 to add up to -2. So this is out. That's not the correct ones. Well, down here, this would be 5x. And then this would be 3x. Well, certainly I can get those to be -2x if the 5x is negative and the 3x is positive. So I would put a negative here and a positive there. So this factors into 3x minus 5 times x plus 1. So even this case is not too bad, as long as that first and last number happen to be prime values. If they're not prime numbers, it gets trickier because you have more possibilities that you could try. So for instance here, 2 is prime, but 9 is not. So there's more possibilities. So you could have, for these parentheses, 2y and y, and you could have 1 and 9. You could have 2y and y, and you could have 9 and 1. Then you could have 2y and y, and you could have 3 and 3. So there's 3 possibilities here. You just have to check and see which ones are going to work. So 1 times y is y, and this is going to be 18y. So there's no way that's going to work. 2y, 9y, you could get 7 or 11. That's no good. Now here, if I take 3 times y, that would be 3y. Then 2y times 3 would give me 6y. And I could get those to be 3y if the 3 is negative and the 6 is positive. So I would need a positive there and a negative there. So this factors into 2y minus 3 times y plus 3. Now, I'm writing this out in detail. Most of the time, students do this kind of in their heads, and that's perfectly fine. I completely understand that notion, and that's what I do. I'm just writing it out here so that you really see the steps instead of just hear me saying what I'm doing. Now this last example, this one's going to be pretty tricky to do the guess and check method because 15 has quite a few factors. 6 has quite a few factors. So the guess and check method is going to take a while to really kind of get through, and you'll probably just give up at some point. There's another way that I go about these, which is actually a little bit more similar to how we solve when the leading term coefficient is not equal to 1. So what we can do, if we look at the product of 15 and 6, that's going to be negative 90. So we're going to look for two numbers that multiply to negative 90 and add up to negative 27. So I'm going to do all my guess and check over here with these numbers here. So I'm just going to start off by listing all the factors of 90. So I could have 1 and 90, 2 and 45, 3 and 30, 4 and 22.5, so that's not going to work. 5 and 18. 6 will divide it, so 6 and 15, and 9. The 7's not divisible by it, 8 isn't either. So then 9 and 10 would give me 90. And then the next number is 10. I've already got it in my list, so I'm good. All right, so I'm looking for values that will add to 27. So 1 and 90, they could be 91 or 89, no good. This could be 43 or 47. This could be 33 or 27. So here, these are my numbers. And I know the rest of these won't work, because this would be, only one set is going to work. The next set would be 23 or 13, no good. This could be 9 or 21, no good. 19 or 1, no good. But to make these work, I need the 3 to be positive, the 30 to be negative. Now, unfortunately, I can't just write x plus 3 times x minus 30. If you check it, it's not going to work. You have to do the factor by grouping process here. So you break this down into 3x minus 30x. And then after that, apply factor by grouping. So 15x squared plus 3x, I'm going to group those together. Negative 30x minus 6, I'm going to group those together. So 3x times 5x plus 1. And here I could factor out negative 6, so that would leave me 5x plus 1. And that's good because this piece and this piece now match. So I can factor that out. That's going to give me 5x plus 1. And the remaining terms are 3x minus 6. So this process is definitely longer than the guess and check. However, if you get stuck with the guess and check, you're not getting anywhere, I feel like this is a little bit more reliable to get an answer. So I do keep this in my back pocket, and I suggest you do the same because you might run into something like this at some point, especially in your homework. Now, I always recommend to start using guess and check. Try a few possibilities. If you're just not getting anywhere, then go with this kind of a method. So in summary, whenever you are going to factor a quadratic, first thing you want to do is look for a greatest common factor. If it exists, factor it out, because that's only going to make your problem simpler. That's always the first thing you want to do. Now, it's rare that you have a GCF, but if it does, it's going to make your life easier. Second, count the number of terms that exist. If you have two terms, you're almost always going to be doing the difference of squares. Sometimes it might be the sum or difference of cubes. Generally, it is the difference of squares, though. Four terms, you're going to be doing factor by grouping. And if you have three terms, hopefully it's a leading term coefficient of equal to 1. If not, maybe it's a special product. But if it's even a leading term coefficient that's not equal to 1, that's still, you know, I've given you a couple good ways of getting around that. Now, I want to answer a question real quick before the end of this video. Students often ask me, why is factoring so hard? Like, why is it such a hard process? Well, the thing is, factoring integer values isn't all that easy in the first place. Like 35. We know the factors of it because we know our multiplication tables. It factors into 5 times 7. So you think, oh, well, that's easy. Well, let's take a number that's not so easy. 357. Well, for me, I don't know initially that that is what the factors are. I know some tricks that could help, like I know if you, like it's not divisible by 2 because the last number is not even. It's not divisible by 5 because the last number is not multiplied by 5. 3, if you take 3 plus 5 plus 7, that gives you 15. 15 is divisible by 3, so I actually can tell that this is divisible by 3. I don't know what times 3, so I would kind of need to come off to the side here and do division. So 3 goes into it 1 time, so that's 3. Bring down the 5. And if we subtract, bring my 5 down to the wrong spot. Bring my 5 down here, so 3 goes into 5 1 time, so that's 3. Subtract, so 27, so 119. And I'm pretty sure that's a prime number. So 3 times 119. There's the factors there. Well, that wasn't so easy. We could try even different numbers. 187. Well, this is even trickier. Like, it's not divisible by 2, it's not divisible by 3, it's not divisible by 4, 5. Turns out this is divisible by 11. That's the first number we run into. This is 11 times 17. It's not an easy process to factor numbers. And we're trying to do this in general. And what I mean by that is when I factor this polynomial, it factors into 2 and 3 if the 3 is negative and the 2 is positive. This represents factors of any number. Let me show you what I mean. So let's let x equal 1. So when x equals 1, I have 1 squared minus 1 minus 6. That gives me, so 1 minus 1 is 1, negative 6. So that gives me negative 6. All right, and if I plug 1 into the factored polynomial, so it would be 1 plus 2 times 1 minus 3. This would be 3 times negative 2. And if you notice, 3 times negative 2 is a factorization of negative 6. So I'm doing a generalization of factoring, which is not an easy process. So it shouldn't be. We shouldn't expect this to be easy. Let's try another number just to make sure I didn't get a fluke with positive 1. So this would be 5 squared minus 5 minus 6. So that's 25 minus 5, which is 20. 20 minus 6 is 14. Now if I plug it into the factored form, 5 plus 2 times 5 minus 3, this is 7 times 2, which is indeed 14. So again, we're coming up with a generalization of a process that's not all that easy in the first place. And it's actually arguably good that this is a hard thing to do, because even for computers, that this isn't an easy process to do. You generally have to go through in order to factor a number that you don't know the factors of, you just have to start with 2, go to 3, then 4, then 5, and see what's divisible. And so even for a computer and a large number, this would take a long time to do. And that's a good thing, because all of our transactions online is based off of security systems and cryptanalysis that's based off of prime numbers, or products of prime numbers that are extremely difficult for computers to factor. And if they could factor them, then people could get access to our transactions online. So the idea that this is difficult keeps us safe online. So it's actually kind of a good thing.